Alright, so you go to a dinner party, and you're sit down next to a complete stranger. Now imagine the impossible. The two of you actually get engaged in a friendly conversation. I know, that doesn't happen. Not to me anyway. But this is just a thought experiment, alright, so let's pretend. Now what's even more surprising, during the course of the evening you find out that both of you share the exact same birthday dates. Bloody hell, that's some crazy coincidence. What are possibly the odds of that? Well, actually, they might be much higher than you think. That is, unless you've heard before about the birthday paradox. Mathematicians calculated that in the group of 23 people, there's a 50% chance that at least 2 will share the same birthday date. I don't know about you, but personally, me and math, we don't exactly get along. In school, math was alright, I guess. That is, until the infinities and imaginary numbers started to appear. From that point onward, it just all went over my head. I mean, how can I take seriously someone with imaginary friends? That is numbers. Imaginary numbers. Anyway, I decided to put the fishy myth behind the birthday paradox to a test. Instead of bothering random people on the street, I created an application which allows me to generate virtual groups of people. Not only it will spare me a lot of social anxiety involved with asking complete strangers about their birthdays for no apparent good reason, but it will as well allow me to automate the whole process, while I rewatch Lord of the Rings trilogy for the 20th time. There's however one little catch. You see, I'm not exactly good at coding. Application itself seems to be running without falling apart, that's not the issue, but I'm sort of expecting my computer case to end up being engulfed in flames at any moment. So, you know, better let's get to it. And here it is. Some parts of the application are covered for now, we will get to them later on. At this moment, this is all we need. So how this works. This box here I call room. Every blue circle in it represents one person. At this moment there are 23 of them. We can change the amount of people in the room easily with these buttons over here. And we can set any number between 2 and 100. The changing box with potential value that you can see here below is actually showing the predicted chance of this room for there being at least 2 people sharing the same birthday date. So this is the number given to us by math that we'll be trying to verify statistically. Here is how. When I click this generate room button, it will assign a random birthday date to every person in the room. Well, technically it will give them a random number between 1 and 365. There are 365 days in the year, so there are 365 possible dates on which a person can be born. That is, if we ignore those special people being born only every 4 years, which we will in this case, sorry. Alright, let's click the button and let's see what happens. We don't have a match. You can see every person in the group has a number now, and all circles have turned red, which means that all numbers are unique. Now let's generate more rooms until we have one with a match. There we go, the circles are green and those have the same number. Now let's have a look on what's going on with those 3 boxes down here. First shows us how many rooms we've visited so far. We have been in 3. And then this box below shows us in how many of those rooms we found a pair with matching birthdays, so 1. Last, for the box, is the chance calculated from the numbers in the first and second box. So, rooms with matches, divided by rooms visited, and then multiplied by 100. So our chance after visiting 3 rooms is 33.33%. Let's generate more rooms and let's see what happens. If I keep on generating rooms, then as the size of our samples grow, we should be getting more and more accurate chance number, and it should start nearing the mathematically predicted chance number. So let's go for 20. Alright, so far it doesn't look very good for the math, but let's make sure. When I was testing this out on my own, I had some sequences in which I had after some 20 tries just about 20%, but in other cases it was up over 80%. Only a really big sample of visited rooms can tell you with certainty if the math works or not. To that end, I made a button, which will click the generate room button for me and it will do so for the set number of times. So let's not mess around and right away go for 100,000 clicks, just to be sure. Let's do this. If you wonder, this is the moment at which I am grabbing a fire extinguisher and I am starting to observe my computer case very nervously. See you in a bit. Alright, well, I don't know. Seems to me like the team with imaginary friends is correct on this one. It's not a completely perfect match with the expected chance, but it is very close. And combined with the fact that we arrived at this number after visiting 100,000 rooms, it makes the result very solid. So there really is a 50% chance that in a group of 23 people, there will be 2 that will share the same birthday date. Question is, how is this possible? The key to the understanding of this paradox is to realize how many possible paths there are in the group of 23, because anyone can share the birthday with anyone else, right? Amount of possible paths in the group is quite simple to calculate, but it is perhaps even better to show it. Here we have a group of 4. At first, we are going to compare the first person to everyone else, so that's 3 paths. Then we compare the second person, but this time only to person 3 and person 4, because we already compared person 1 and person 2 before. So this is another 2 paths. And now we just have left to compare person 3 to person 4 and we are done. This leaves us with this descending equation 3 plus 2 plus 1 equals 6. And that's the number of the possible paths in the group of 4. Now for a group of 23, you can do it in the same way, like add up all the descending numbers going down from 22 to 1, or alternatively, take 23, multiply it by 22, and then divide it by 2. And this will give you the same result, which is 253. Number of possible paths grows rapidly as the size of our group increases. In a group of 10, there are only 45 possible paths, but in groups of 100, there are already 4,950 combinations. In fact, when I click on a generator button with this size of a group, the program has to do all 4,950 comparisons each time. And this is why I keep a fire extinguisher nearby. Very curiously, scientists believe that this number is one of the main reasons why our brain has evolved to be as efficient as it is. As before the dawn of the civilization, there weren't many mentally challenging things to do. But social interaction was an exception. Back then, your life could depend on the understanding of the social dynamic within the group that you lived in. You had to know who to trust, who you can depend on, and whom you can't, and so on. But you needed not only to understand others' relations towards you, but also all the individual relationships between every member of the group, back and forth. And our brain can keep track of all of those. In a group of 100, it is 4,950 relationships, but it is known that humans can still efficiently cooperate and keep close relationships, even in a groups of up to 150, which gives us 11,175 individual relations. But back to the birthday paradox. While the number of possible paths within a room gives us a good idea of why the chance for matching paths is so high already in such a small group, question still remains as to how the chance itself is actually calculated. There are 365 possible dates a person can be born on. If we simplify it a bit, each time a person is born, it is like there is a dice thrown, just this dice has 365 sides instead of 6. So in a group of 23 people, there will be a dice thrown 23 times. And if it lands twice on the same side, we have a match. Now, how to calculate the chance of this happening? It is actually easier to compute the complementary situation. That is, what are the chances of all people in the room having different birthdays? Or, in other words, to stay true to our example, what are the chances that all dice throws will land on different sides? Because the outcome of this is mutually exclusive with the outcome we truly seek, calculating one will get us the answer to the other as well. So, our starting point is what are the odds of no one having the same birthday in a room with one person only? That's 100% or 365 in 365 cases. Because one person can have a birthday on any day of the year without worrying about a match. But when you have 2 people, the first can still have a birthday on any day of the year, however the second person needs to have a birthday on any day of the year, but that one on which the first person's birthday already is. So that is 364 in 365 cases. Now, to calculate the chance of them not having the same birthday, we need to put the 2 odds together. For that we simply have to multiply the 2. 365 divided by 365 is 1, so we can ignore it. 364 divided by 365 is 0.9972. If I multiply this result by 100, we'll get to know the percentage chance for no one sharing the same birthday in a group of 2, which is 99.72%. Now you just need to calculate the complementary situation. So 100% minus 99.72% equals 0.28%. And this is the chance of there being a match of birthdays in a room with 2 people. What we employed here is called conditional probability. That's something you use when you need to compute the odds of several events happening in succession. First event was person having a birthday. Second event was another person having a different birthday than person 1. Third event will be at another person having a different birthday than first person and second person. And so you will continue until you have 23 events representing 23 people, or whatever the size of your group is. And this is how we calculate the chance behind the birthday paradox. With this, we have sufficiently covered everything there is to the birthday paradox. Now we can take a look at different things this application keeps track of, and which I thought to be somewhat interesting. So, this one here records the average number of pairs per room. This is more interesting with larger group sizes, as in those there will be usually more pairs per room. Let's try a room with 80 people. I will click the generate room button and there are 9 pairs in this room. So our average after one room is 9. Now let's get a more accurate number and do a sample of 1000. That should be enough. And this lets us know that in a group of 80 people we can expect 8.6 pairs on average. Another 2 boxes here at the very bottom keep track of the longest successive streaks. That is how many rooms there were in a row with a pair or with no pair. Let's go back to 23 people in the room. That gives us a chance of 50%, which is the same as a coin toss, right? So when we will take again a sample of 100,000, those 2 boxes will pretty much tell us what was the most time a coin has fallen on the same side in succession. It is a bit crazy to see, but at one point there was a streak of 18 and 17 same outcomes in a row, while the chance was 50%. And last but not least, there are several boxes under sample button. Those boxes recall some properties of the sample just taken, and they allow us to track accuracy of the selected sample size. First box keeps track of how many samples were taken so far. The box to the right shows us a chance for a match from the sample taken most recently, like this. In the bottom line, 2 large boxes record the unluckiest and luckiest sample taken, while the box in the between shows the difference between the two. Now, why does this matter? Let's say that we are conducting a research and you're trying to find out the effectiveness of some pill against anxiety or whatever. To get a really reliable number, you will have to try it on as many people as possible, because it is really not the same thing if you get 90% after 10 tries and 90% after 10,000 tries, because during 10 tries you can just get lucky. This might sound like a no-brainer, but it is a mistake often committed. That is, generally not by scientists and researchers, as they are aware of the small sample size errors. But who gets fooled by it, again in general, are influencers, journalists and politicians. So, unfortunately, those that are communicating with the public, and they might start to, for example, champion some cure that successfully cured someone, but was, all in all, tested only on that one person. You probably witnessed something of the kind during the recent pandemic. Anyway, this is what the application allows you to test out, as it records the luckiest and the unluckiest sample taken of that size. Results will let us know how far away from the real chance you can end up, if your sample size is just this small or this big. To compare the accuracy of the sample size, we'll have to take several samples of each size. To that end, I created a button. And this button will be clicking the sample button, while the sample button clicks the generate room button. So when I click the sample button, it will actually go through all the available sample sizes, set amount of time. There are 5 sample sizes, 10, 100, 1000, 10,000 and 100,000. So when I click the sample button right now, it'll go through all the sample sizes once. But to get a decent sample of all samples, let's go for 25. This will take a while. Once this is over, it will get us somewhere to 3 million rooms. Give me a moment. Alright, let's do this. Nope, I'm not going there. So, 2,700,000 rooms visited. Measured chance is perfectly aligned with the predicted chance. And would you look at that, there was a streak of 22 rooms with a match in a row. That's something. Now let's check the differences between the luckiest and unluckiest samples of each size. And as you can see, with each increase they are getting more and more precise, and the difference between the 2 peaks thins out. Now, it is more of a question of how precise your research needs to be. If it is tolerable to be possibly about 5% of the mark, a sample of 1000 might be already enough. Where this is, among others, applicable, and what everyone watching this video should be somewhat familiar with, that is unless you live in North Korea, are political election pools, or rather a political election pool's errors. To get accurate pools, you need to get as big a sample as possible, and such a sample that will properly represent the whole spectrum of voters. Despite the best efforts, pools tend to be very often wrong. but usually they are within the 5% error tolerance, which does not give us much, because major elections are scarcely decided by the margin of 5%, so polls in such cases are hardly better than rough guesses. Anyway, that's it for this video. Thanks for watching. If you want to try out the Birthday Paradox Simulator on your own, you can get it from the link below. Use it at your own risk. Application is as well available right in your browser, or you can download it on Windows, Mac and Android. For iPhone though.